Let's look at part 2. In part 2, we have this formula for Lambda-Jones potential, and to find the minimum point, we can just let x to be r naught divided by r to the power of 6, because we realize in this case this potential energy will just be x squared minus 2x, and we know that this has a minimum at x equals 1 because we can rewrite it like this. So we found that at the minimum is at x equals 1, which means that r naught divided r equals 1. So it will have minimum when r equals r naught. Then let's try to plot this thing in decimal. So to go to decimal, let's open your favorite browser and let me key the equation in again. So we want to set u naught to be 8, r0 to be 1.5. We have power of 12 and then minus 2 times the same stuff to the power of 6. So here's how the graph look like, and we can set the axis. We want to set it from 0 to 5 minus 10 to 10, 0 to 5 minus 10 to 10. So here we have our Lambda-Jones potential. Good. So now let's look at the lowest point. The lowest point is at here, and you can see that it is at 1.5. So indeed, the minimum point happens when the r is 1.5. Good. Now we can try to match the potential energy to a spring potential energy close to the lowest point. Let's zoom into the lowest point. It will be at somewhere around this is somewhere around 1.5, so 1.49 to 1.51, and somewhere around minus 8, so minus 8.01 and minus 7.99. Good. So in this range we can see the very bottom of the Lambda-Jones potential. And then let's see if we want to add, we can try to add another potential energy that represents the spring. So let's do the spring potential energy. Use S is the spring. So 1/2. Let's set x to k to 1 first, and then x minus, right now the equilibrium position is 1.5 square, and then the minimum potential is 8. So it looks like flat line, but it's because that we didn't set k to be big. If we let k to be bigger, and let's say let k be bigger, and now you see we can adjust k so that they look similar. So we get k is about 260 for this graph. And we can actually calculate it with the formula we have. So k will be the second derivative of potential energy. Right now the function is a function of r, so let's differentiate with respect to r, and it should be the second derivative at the lowest point. So let's do that. The potential energy we have is this thing, so it is the second derivative of 8 times 1.5 r 12 minus 2 1.5 r 6, and at r equals 1.5. So let's get 8 out of the parentheses, and the whole thing is, alright, 1.5 to the 12 is a constant, and we're differentiating r to the minus of 12 here and r to the power of minus 6 here. this is just a polynomial. We will get a minus 12, and minus 12 becomes minus 13. Let's keep it constant, 1.5. And here we have also a 12, and 6 becomes 7. 6 stays the same. 8 times 12 is 96. And then we can differentiate it again to get another minus 13. Here's 14. This is a constant. So we have minus 7 from differentiating r to the power of minus 7. And 1.5, 6. And we want to set everything at r equals 1.5, 1.5, r equals 1.5. So after we do that, we'll get 96 times 6 and times 1.5 to the power of minus 2, because here's 14 and here's 8. They are all two numbers bigger than the denominator's power. So this will give us 96 times 6 divided by 1.5 divided by 1.5, 256. So the exact value is 256, which is very close to what we get up here. We've just measured the graph. So to calculate frequency, it is k divided by m. We get k is 256, m is 4 kilogram according to what we have here, 4 kilogram. And because everything else is in SI units, so we know the k we get by this differentiation will be in unit of Newton per meter. So this is totally fine. This will give us 64, which means that the angular frequency is 8 radians per second.